It's how we weigh tasty snacks. Mmm, Jaffa cakes. Aren't you nature's natural candy? Technically from the UK or something. Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might
Yeah,
be just hyper Rulial Turtles all the way down.
Yes, it's on the back of an infinite number of hyperrural turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So what are we talking about today? We're talking about the kilogram. Why did I make my previous statement? Well, all I know is back in the day when I would buy candy, they'd usually have the grams and stuff like that, and that's like 1/1000th of a kilogram. I'm like, why do they list it like that? I don't know. Maybe it makes us feel like it's smaller or something like that. All I know is my chemistry teacher, when somebody was trying to sell her some candy for a fundraiser, she's like, I'll take whatever has the highest mass. And that really stuck with me. And who doesn't like tasty snacks? But I see you there. Oh, welcome there. Spartan, thank you for joining, my friend. Good to see you. But what are we talking about? Well, let's bring up our good friend Wikipedia here. Again, take it for what it's worth. Links to everything are in the doobly-doo below. So, the kilogram is the base unit of mass in the International System of Units, SI. Having the unit symbol kg is widely used measure in science, engineering, and commerce world, and is simply called a kilo colloquially. It means 1,000 grams. I know. And then we had all these things before, these little measures and everything. So essentially, long story short, to the best of my knowledge, is back in the day, what do? We created these units and we called them the kilogram. And then one of them got locked up in, I think, like France. And so we had to send them all around. And then over time, they kind of slightly degrade in there. So basically, they redefined it and everything. I think it was when we looked into it, it was about 2019. They did the redefinition of the kilogram. It should get into it right here. So the kilogram is defined in terms of the second and the meter, both of which are based on fundamental physical constants. Wait, hold on. They're saying something that we use to measure mass is based upon a unit for time and length? Neat. This allows a properly equipped meteorology laboratory. What is meteorology? Like meteorology. That's what I see there. It's a study of measurement. Oh, it's exactly what it sounds like. There we go. To calibrate a mass measurement instrument such as the kibble balance. Oh, well, all I know is we do sell a lot of dog food at work, or at least I stack a bunch of pallets with it. I apologize for the insider information. It wasn't like dogs. Uh, Not all. As the primary standard to determine an exact kilogram of mass. Okay. So it was originally defined as the mass of 1 liter of water, so that's cool. So when you actually get into it down here, defined in terms of those units, the kilogram is formulated as, so it looks like the speed of light squared, and that's, what is that? Oh, I think that, no, that's Planck's constant, isn't there? Yeah, it's the sixth one. And then that's the speed of light, or okay, basically they have them all in there. So basically, all right. So reduce Planck's constant times the delta change in v. See, I didn't actually look at that ahead. Okay, it's the mass remains within 30 parts per million of the mass of 1 liter of water. So that's actually pretty dang good. So groovy. All right, meters per second. Cool. Okay, so essentially, what we're looking for here is we're looking for its relationship to what we did yesterday, the AMU, the atomic mass unit, also colloquially called the Dalton. So, as we can see here, NIST, our friend over here, the kilogram atomic mass unit relationship. A numerical value we're looking for is 6.022140761. error bars of 18 for those last two digits there, times 10 to the 26 U. It's shorter there, and again, nobody would ever confuse notation, especially when you get a lot of different things. Not like in corporate America, we have all these acronyms for literally everything. Not all. Okay, so we got that there. All right. So how would we go about this? So again, as we have on the thumbnail there with Son Goku holding nap, I should have actually had that be the AMU and the kitchen or whatever it was be other. It's okay. These are how these things come to my mind. Okay. So in order to geometrically derive the kilogram, to try to figure out maybe, I don't know, a little additional assistance to figuring out our persistence, we basically just invert what we did yesterday. So yesterday, this was on top, our 3 square root of pup there, the universal parabolic constant. So basically, circle basically has 3.14159, yada, yada, as its ratio to the diameter. Cool. This just happens to be for parabola, that thing that comes down on like that graphing calculator that just goes, yeah, so that was on top. This is on bottom now. And then we have 4 Joe1 cubed. Again, what is a Joe1? We go to our friend Wolfram alpha. And again, this is the hyperbolic vortex equation right here. Again, links are down there. So what is this? This is basically one of our primary equations to help derive the constants of nature. It's 1 over x plus x cubed divided by 2 pi. We set that equal to I raised to the I, and that's all raised to negative pi divided by 2. We subtract out our lambda here, which happens to be the Planck mass gap. And then it gives us these answers here. The first answer of which, when we square it, let's do it right here. This gives us what we colloquially know as the fine structure constant. All the non-controversial digits. So if we just type in fine structure constant, what we got here? 0.00007, if you would, 72973525729555. It's a geometric derivation. We can go as far as we want. Okay. The fine structure constant according to Wolfram alpha. 0.00729735257. Oh. 257. Oh, and it keeps on going. And again, there is some debate on the last. They have some other things there, but those are the uncontroversial digits. But hey, Rick, thank you for joining, my friend. Good to see you here. And okay, so that's basically what a Joe1 is. And we have our other, and again, we have Joe2. It's going to be using that as well. As that's essentially basically the second fine structure constant. They basically have 4 of them here in different forms. Who knew? The only reason that kind of noticed is he just got the first answer. He's like, oh my god, I found what I was looking for. This is amazing. And he's going through doing derivations like, wait a second, this number looks familiar because it was just coming up in Wolfram alpha just as this number. He goes back, he's like, wait a second, that's one of the other answers. Nature sure is. You go back here, we'll finish this up. So basically what we do is we have our 4 Joe1s cubed, divide by 3 times the square root of the universal parabolic constant. And we multiply it by our boundary condition. In this case, it happens to be the mass of the electron, except it's 1 over the mass of the electron. See, we're continuing our inversion pattern here. We multiply it by our terminal action here, which is 1 plus or minus. And this time, instead of plus, we do minus. So it's 1 minus 1 over the lemniscate constant. So basically, the infinity symbol or the figure 8 that we had there. Because again, that actually has a constant as well, like pi and like pup, the universal parabolic constant. And we multiply it by Joe1 minus Joe2 just those numbers that we had there. Literally, you just copy and paste them in there. And we multiply it by our inversion boundary there, which happens to be the Planck mass times the Planck length divided by the Planck charge squared, which coincidentally comes out to be 10 to the negative 7. A very interesting thing. I know Rick had brought that up the other day. So let's actually go over here. So just because we can, blank. I know there's some new folks out there too. Blank mass, blank length, Planck charge, and then since we're going to divide by it, we do -2 for our exponential there. So look. Oh no, it's trying to give us a list. No Wolfram alpha, we want multiplication. Here we go. Oh, what's this? 1 times 10 to the negative 7. That's very interesting. Groovy. So we take that there, and we just plug it into our friend Wolfram alpha over here. Again, links are in the doobly-doo. So what do we have here? We have 4 times Joe1 cubed. That's divided by 3 times the square root of pop, the universal parabolic constant, times 1 over the mass of the electron. And again, we have that derived over. Oh god, I have the polygamma form in there. That's basically just the hyperbolic volume of the figure 8 knot right there. You can literally just type in figure 8 knot. We'll just show why. Because Wolfram alpha is freaking fantastic. So figure 8 knot hyperbolic volume. Wolfram alpha does the number crunching there for us. Oh god, I changed the. Oh god, I forgot. I'm supposed to have the 2 there. What a noob. I threw all the stuff in brackets. There we go. Oh look, it's the same number. Groovy. Cool. So we got that. Yep, mass of the electron, 1 over that times our terminal action over here. So basically primary action, boundary condition, terminal action, 1 minus what we had yesterday, 1 over the Lemniscate constant, the figure 8 constant we have over there. I actually typed it in there. So it just says 1 over big O. And then we throw in brackets there, our J1 minus J2, and we multiply by the 10 to the negative 7 in this case. We just divide by 10 to the 7 there. And it gives us this number right down here. Okay. So what were we looking for? Go to our friends at NIST. Number we're looking for is 6.022. 6.022. 140. 140. 7621. 76. 18. We are off. Yes, that is correct. But we again must remember we do have error bars on that. That's 18, so that could go up by 1, and that. So basically, what is it? We had 2 1, where we had like 1 8. All right, so it's off by 0.3. The error bars. All right, so we're off by 3 for the last 2 digits. The error bars are 18. My friends, this appears to be a geometric derivation of the kilogram. Well, at least that's the claim. That's the conjecture. Yes, I know, Rick. 10 to the 7. That was a very interesting hint you gave me there, and I'm starting to notice more. I need some more. I'll have some time over the next year while I'm exploring this basically full time. Well, at least that's what we're gonna shoot for. But yeah, that's all we got right now. But it's amazing that this worked, and that was one of the things. Last time I was at the monastery, Dad would just like literally come down. And he's like, all of a sudden he's like, "Oh, this is hard. I'm trying to figure out the boundary conditions." Also, he's like, "Yeah, I solved like 6 of these before breakfast." It's like, what? Yeah, because once you find out the configuration, it's like, well, I mean, this next concept that I have listed on NIST very often it's just an inversion of the other one. So you just put one over in certain places, and if you do it enough, you start to see patterns. Even a noob like me is starting to notice patterns. Are they right? I don't know. I guess we're gonna have to wait for experiment to bear out. But that's all we got for right now. Peace out. Take care of yourselves, everyone. All I know is it's a wacky and wild world out there, but I'm rooting for us because I think we got this. Why? Because we can.